In the last class, we learned about the predictive maintenance of acoustic stacks in order to predict their failure through the monitoring of their frequency. This is class 2 of the maintenance module. Here, we will talk about Preventive Maintenance 1, which corrects the degradation of the interface and restores the coupling between the stack elements, which in turn restores part of the tuning and mechanical quality factor. Shall we start? If during predictive maintenance we verify that there is a frequency deviation greater than 0.25%, we know that the stack is out of the acceptable frequency range and probably operating with low efficiency. Furthermore, the stack elements are possibly with reduced coupling due to degradation of interface and wear of contact surfaces. When that happens, something needs to be done. Otherwise, the low efficiency will cause the stack to heat up, accelerating the degradation of the interface and the frequency deviations, which can generate more serious problems such as generator overload or burning transistors. But what can we do to deal with this problem? The first step is to perform Preventive Maintenance 1 to restore the interfaces, restoring the coupling and correcting part of the frequency deviation. In Preventive Maintenance 1, we first disassemble the acoustic stack and remove the studs to visually inspect the element's interface. Despite the robust appearance of the acoustic stack, we need to take it apart with great care to avoid damaging the surfaces when we handle them. Any dents or scratches or any damage at all to the surfaces will affect the stack performance. As well as affecting performance, superficial damages are regions of stress concentration and crack nucleation during vibration at ultrasonic frequencies and high power. This means that the ultrasonic vibration on the stack may cause the crack at these damages. In an ultrasonic stack with superficial damage, the energy dissipation at the interface causes heat and fatigue, while the superficial damage causes stress concentrations. All this combined can lead to cracks in the acoustic stack elements. That's why this care is necessary during the maintenance of the stacks. We must clean its interfaces with a clean paper towel or cloth and solvent to remove all dirt and grease. We also need to clean the studs with a brush or ultrasonic cleaner. We then inspect the interfaces of the elements of the stack, checking them for wear and grooves. This wear is normal and occurs simply by using the stack. However, as we learned previously, this damage and wear reduce the contact surface and decrease the ultrasound transmission efficiency at the joint. All of this reduces the coupling between the elements and causes stress and heat, affecting performance and frequency. So, what should we do when the acoustic stack elements' faces are worn out and grooved? We must restore the interfaces. To do this, it's necessary to sand the worn interfaces until they are flat again, until all the grooves are removed and a smooth and clean surface is obtained. It's important to use sandpaper above 400 grit to ensure the best finish possible. If the element's contact surface is badly damaged, we can start with a 208 grit sandpaper. But as soon as we restore some of the flatness, we should increase the sandpaper grit. Moreover, the elements must be sanded on a flat and smooth surface. To ensure a good support surface, we recommend the use of a granite surface plate. A 40 by 25 by 7 cm class 0 surface plate is sufficient and cheaper than a new ultrasonic component. An acceptable workaround is a mirror. We must tape the sandpaper to the surface plate. For sanding, we recommend stroking the element twice in the same direction and afterwards rotating it a third of a turn. Then, repeating these movements until the element interface is restored. Another way that can be done is the H-shape move. It is essential to prevent the part from tilting during movements, as the interfaces must be parallel as well as smooth. The weight of the part itself must be enough to apply the necessary pressure during the process. If we tilt the part during sanding, we may round the corners of the part, which would be even worse than having scratches. From the fundamentals, we learned that changing the dimensions of elements affects their frequency. Sanding the interfaces shortens the element, right? Shortening the element increases its frequency. The consequence is that restoring the interface too much will affect the element performance. Therefore, we must restore the interfaces the least possible, and also only when we detect frequency deviations greater than the tolerance of the welding machine. Thus, we avoid unnecessary dimensional changes. As well as restoring the interfaces, it's necessary to inspect studs, threads, and everything else to find and restore or replace damaged parts. Although not mandatory, it's advisable to use an ultrasonic cleaner to clean these parts, as it also cleans hard-to-access regions as threads and holes. Later on this course, we'll learn about the recommended tools for these procedures. Once all the elements of the acoustic stack have been restored and cleaned, we need to reassemble it. Reassembly must be done with controlled torque, always following the manufacturer's instructions. If there are no manufacturer's instructions, the suggested procedures are as follows. Firstly, before reassembly, apply a thin film of high-temperature molybdenum-based grease or high-pressure silicon-based grease to the matching surface. This way, we protect the coupling surfaces to reduce the rate of degradation with use. Make sure that the film of grease is thin and the application is only in the interfaces, never on the studs or on the thread. If we apply grease to the stud, the parts may come loose during the use of the equipment. Secondly, insert the studs into the sonotrode and booster, then apply a torque of a maximum of 20 Nm as recommended in this table. Thirdly, mount the converter on the booster and then connect the converter plus booster to the sonotrode or horn, always taking great care to not scratch or dent the element surfaces. For reassembly without the manufacturer's instructions on the applied torque, we can use the reference values from these tables. In this table, we find the recommended torque according to the frequency of the machine to reassemble and tighten one element to the other. So if the frequency of the machine is 20 kHz, we have to apply 35 Nm. If the frequency of the machine is 30 kHz, we have to apply 25 Nm, and so on. Note that the recommended torque is low. What enables this low torque is the restoring of the jointing interface, done in the previous steps. As the surface is clean, smooth and flat, it's not necessary to apply too much torque. Here, an important observation. It's common for users of ultrasonic machines to retighten the stack, increasing the applied torque as it starts to show lower efficiency because of wear. And often it works, doesn't it? But what happens when we apply more torque is that we correct the poor coupling and surface wear by crushing those grooves and scratches with the high torque pressure. This excessive pressure stresses the stack and the stud unnecessarily. Therefore, over-torquing must not be used for interface wear compensation. Applying a low torque is desirable because the more torque we apply on the stud, the more unnecessary stress we put on the stack elements and on the stud itself. This increases the tension concentration on the parts that may cause damage to either the stud or the elements. See in this video an example of consequences of excessive torque. Other typical damages caused by tension concentration are the cracks in the elements around the stud region and the stud breakage itself. After reassembly, the frequency deviation should have been reduced. If it has not reduced, maybe there a defective element. In this case, we should perform a preventive maintenance too, which we'll learn ahead. But we are not done here yet. Now, we know how to do preventive maintenance 1 to keep the coupling of the stack's elements optimized. However, to perform the procedures, it's necessary to use suitable tools in order not to damage the stack during the restoring process. Remember, defects in the stack element surface can affect its performance and are correct nucleators. Custom vices for acoustic stacks are recommended. We can find some at the link below. As an alternative solution, we can use a 3-jaw lathe chuck for cylindrical sonotrodes or for the booster. It's important to cover the jaw's contact area with some soft material to avoid grooves. For example, put a piece of paper between the sonotrode and the 3-jaw lathe plate. Suitable wrenches are also essential, and a torque wrench is indispensable. In this picture, there are special torque wrenches. These are excellent tools, but in some countries or regions, they may be expensive and hard to find. In this case, an alternative is to adapt a standard wrench by soldering a torque wrench socket to it. After coupling the torque wrench, we have an adapted torque wrench. But this adaptation has a side effect, which is to increase the lever arm, because the support point that was the torque wrench connection has become the center of the wrench contact. This math works around the problem. Here, Ts is the value of the torque to be set in the torque wrench. Tw is the value of torque that we wish to apply to the stack elements. L1 is the distance from the center of the handle to the support of the torque wrench, and L is the distance added by the adaptation made. To make it clear, let's apply the formula in a practical example. Imagine that you are going to assemble a 20 kHz stack. We saw previously that the suitable torque to be applied is 35 Nm. In addition, for the torque wrench in the example, the distance between the handle and the center of the torque wrench coupling, that is L1, is 40 cm. The distance added by the adaptation, or simply L, is 90 cm. So, by applying the equation, we have torque to be set, Ts, equals 35 times 40 divided by 40 plus 9, which results in the torque set of 28.5 Nm. This means that to assemble a 20 kHz stack using the torque wrench of the example, it's needed to set the torque wrench to 28 Nm. With this configuration, I'm going to apply the 35 Nm indicated for 20 kHz stacks. In the next class, we will learn about preventive maintenance 2, which allows for identification and treatment of the device element when all the actions of this class were not enough. See you there!